Okay, pleasure to start the third lecture of Henrique on Introduction to Poisson Geometry. Today, Lie algebroids and symplectic groupoids.
All right, so let's keep on going with this. So just a brief reminder of what we saw in the first two lectures. Feels like it was a long time ago to me, but so we went over the two definitions, two viewpoints to Poisson structures based on brackets and by vector fields. We talked about some related structures like Hamiltonian vector fields. I gave a bunch of examples. I explained a bit the local theory of Poisson structures. There is one central theorem, which is the splitting theorem. And there you can see that there's also, there's a symplectic foliation associated with any Poisson structure. And also some transverse geometry. And towards the end, I spoke about some invariants that are relevant in the theory of Poisson manifolds. So today what I want to do is bring Lie algebroids and groupoids into the picture. Okay? And so that's a plan for today. So basically, there are two historical motivations to consider Lie groupoids in connection with Poisson geometry. One has to do with quantization, and the other one with the symplectic realization problem. And I will follow the second path. So I'll explain a bit what symplectic realizations are and some recent, some classical problems, some recent progress. And this will lead us to groupoids and algebroids. So I'll, briefly remind you of what these objects are. These will probably be boring for those who know what Lie algebroids and groupoids are, and possibly not very useful for those who don't know at all what groupoids and algebroids are, but I'll do my best to at least, highlight the main points. And then I'll go back to Poisson geometry and tell you about the connection about Poisson structures and Lie algebroids. There are a few connections. And then hopefully I'll get to symplectic groupoids. Okay. All right. So let me start then with this problem of symplectic realizations. So the starting point is a Poisson manifold, and the definition is the following. A symplectic realization of a Poisson manifold is just a Poisson map from a symplectic manifold to it. Okay, and I'll call it full if this map is a surjective submersion. So remember that, one way to produce Poisson manifolds from symplectic manifolds was to consider a symplectic manifold, a nice group action by symplectomorphisms, and go to the orbit space. So the orbit space inherited a Poisson structure naturally, and the quotient map was a Poisson map. So the idea is, to wonder about symplectic realizations is to try to understand if given any Poisson manifold, you can realize it as the quotient of a symplectic manifold. Okay, why? Because symplectic manifolds, from the point of view of Poisson geometry, they're much easier, right? The foliation is only one leaf and stuff like that. Okay. So, you can think of the idea of desingularizing, a nasty Poisson structure into something non-degenerate. Okay, so yeah, so let me go over some examples. So this is not working, right? It should just, oh, okay, now it is. Okay, so let me give you some examples of this symplectic realizations. So the first general remark is that without the fullness assumption, any symplectic leaf of an arbitrary Poisson manifold is an example of a symplectic realization. Except that, the fullness condition is not satisfied. I'll be mostly interested in symplectic realizations which are full. Okay? So the trivial case, which is a Poisson manifold with a zero Poisson structure, has a very simple symplectic realization, namely the cotangent bundle of the manifold with the canonical symplectic form and the canonical projection. Yeah. Okay, that's a symplectic realization. And another remark is that if you consider, for example, Rn with a zero Poisson structure, and a symplectic realization from a symplectic manifold of dimension 2n. Oh, this is bad notation, right? So let's say a symplectic, and I'll just put here dimension s equals to n, so that doesn't look like a sphere. With some symplectic form, then a symplectic realization is the same thing as a collection of n functions which Poisson commute with one another, right? Which is what is called an integrable system. Okay, so finding symplectic realization, so you can see an integrable system as a symplectic realization of the trivial Poisson structure. It tells you that there's already something interesting there. And the other example where this is relatively simple to describe is, remember that a class of Poisson manifolds was obtained from Lie algebras, the so-called linear Poisson structures. So if you have a Lie algebra, then you can consider its dual and wonder about symplectic realizations of that. Okay? Now here's one thing. If you choose a Lie group whose Lie algebra is the one you're interested in, then you can immediately produce a symplectic realization of that by taking the cotangent bundle of the Lie group with the same canonical symplectic form. And now, as the map, either left or right translation. Remember that this guy can trivialize it by left or right translation. That this only amounts to signs. Let's not worry about that. Let's say left or right translation. So this is actually a very important theorem in mechanics. Okay. So this already indicates that there is some connection between finding symplectic realizations and integrating something, right? So in this case, I took an integration of the Lie algebra and I managed to find a symplectic realization of a related Poisson structure. So this will be more clear once I introduce Lie algebroids and groupoids in the general case. Okay, and perhaps something else I could say is that more generally, to give you more reasons to believe that symplectic realizations are interesting, again, if you take the dual of the Lie algebra as your Poisson manifold, and you consider symplectic realizations from any symplectic manifold, we call it mu, I claim that this is the same thing as a moment or momentum map that already appeared in Jonathan's talks, lectures, right? So usually a momentum map refers to an action. You have an action and the action admits or not a momentum map. But what I'm saying here is that out of this information, at least at infinitesimal level, the action is already defined. Okay? So basically, let me write here, sorry for that, but like what is the action that is encoded here? So if you dualize this map, right? Remember that you can see the Lie algebra as, as inside the functions on G star. Okay, so if you dualize the map, this guy becomes this, and from here to vector fields on the manifold, we just can take the map that associates the Hamiltonian vector field to a function. So this composition, as long as this map, is a Poisson map, is a symplectic realization, this will be a Lie algebra morphism, and therefore will define an action for which this is the moment map. Okay, so I'm just saying that, n that is equivariant, blah, blah, blah. Except that in principle may not have the Lie group around, but doesn't matter. I'm just saying that, symplectic realizations are moment maps for the dual of a Lie algebra. Good. And one of the questions that I would like to address is whether, in general, I can see an arbitrary symplectic realization as the moment map for something. And the question is for what? Okay, and that's where the symplectic groupoids will come in. Okay, so one of the messages is that any Poisson map like this is a moment map. You just have to relax a bit your idea of what an action and a Hamiltonian action is. But there's something that acts there. Okay, good. All right. So there is one property of symplectic realizations that is kind of interesting. So basically, they don't appear by themselves. So whenever you have a symplectic realization, there is an additional foliation in the story. Okay, so if you have a symplectic realization, then I'm claiming here that, let's suppose this is S, and that's your map to M, and these are the fibers of your map mu. If you look at the symplectic orthogonal complement to the fibers, let's write them here, and not necessarily a complement, but I'll just write them like this. Then it turns out that this distribution is constant rank and involutive. Okay, so there is another foliation in the story automatically. Okay, so the fact that this guy is involutive, that this distribution is involutive, is part of what is called like Lieberman's theorem, which is a problem in the problem set. Okay, so you check that. Okay, and under favorable circumstances, if the leaf space of this foliation is nice, right, then there will be a second manifold, the leaf space, that will appear in the story. And again, by Lieberman's theorem that you're going to prove or have already proven in the problem set, there will be some structure here. Okay, why? Because the symplectic orthogonal of these fibers are the fibers of mu, right? And this is involutive, and that's what the problem is about. Okay, so modulo this regularity condition, there's a second Poisson manifolds naturally in the story. Okay. Yeah, I'm sorry, that's right. I'm talking about, a full symplectic realization. Absolutely. Yeah, so it's a surjective submersion. Thanks. Okay. Full. Good, so this takes me very naturally to the notion of a dual pair of Poisson manifolds. Yes?
Sorry, in your previous example, what is the reason why
No, I'm assuming that this is a Poisson map. What does that mean? It means that this guy is a Lie algebra homomorphism, and so is this guy, and so is the composition. Yeah. Right. So this is already a concept that was present in this original paper by Alan Weinstein from 1983. So he studied symplectic realizations there. And, he arrived at this concept that, in certain situations, you may have two different Poisson manifolds, which are realized by the same symplectic manifold. And he also noticed that this is actually a pretty interesting thing in the sense that it really relates the Poisson geometry in M1 and M2. The Poisson geometries are quite related. So what he noticed was that, at least in the case of a full dual pair, if the fibers of mu1 and mu2 are connected, then you get a one-to-one correspondence between symplectic leaves. M1 and M2 may have different dimensions, okay? But there's a correspondence between the leaf spaces. Okay, so how do you do that? You take a symplectic leaf, you take its image, project down here, and you get a symplectic leaf of the other. Okay, and he also noticed that, if you take points that correspond in a dual pair, so if you take a point in S, here's M1, here's M2. So if you take a point here, mu1 of P and mu2 of P, that the transverse Poisson structures here, they are perhaps up to a sign isomorphic. Remember, like the leaves are in correspondence, right? So to the leaf here, there corresponds a leaf here. Now you can look at the transverse direction, and they are isomorphic. Perhaps up to a sign, whatever. Okay? And of course, so are their linearizations. So like this transverse, this isotropy Lie algebra that we found on any, transverse to any symplectic leaf, they are isomorphic. Okay? So the story here is that, this kind of correspondence, looks like that it really captures just the transverse geometry. So if you want to understand the Poisson manifold, or Poisson geometry up to symplectic leaves, then this is like a nice way to make them correspond to one another. If this was an equivalence relation, but if you want to turn that into an equivalence relation, you have to impose more conditions to be able to compose these diagrams and things like that. But that can be done, and this leads to a weaker notion of equivalence in Poisson geometry called Morita equivalence. And you can study the self-equivalences of a Poisson manifold with respect to this relation, and that's called the Picard group of the Poisson manifold. Something that I defined with Weinstein many years ago and then studied with Rui Fernandes. Here's some examples. Good. And again, a prototypical example of these dual pairs that was, one of the motivations for Weinstein, really came from the theory of Hamiltonian actions. So whenever you have a Hamiltonian action, then you have a diagram like this. So let me try to keep on calling my symplectic manifolds S. So whenever you have a Hamiltonian action on a symplectic manifold, then you have a moment map. And if the action is nice, free and proper, you can consider this other Poisson map into the orbit space, which is a Poisson manifold. Okay? And, and the fibers here will be the symplectic orthogonal of one another. And this is an example of this dual pairs, perhaps not full in principle, but if the action is locally free and you restrict yourself to the image of the moment map or something, this will be okay. Okay? So this is saying that, okay, so what is this correspondence between symplectic leaves in this concrete example? So what are the symplectic leaves here? I told you last time. These are the coadjoint orbits. And what are the symplectic leaves here? This is a problem in the problem set. These are the Marsden-Weinstein reduced spaces. And what is the correspondence? It's Marsden-Weinstein reduction. You take a coadjoint orbit and you do the reduction with respect to that orbit, and you find a leaf of this guy, modular connected components or something. Okay? Good. So, one of the points is that, a bunch of theorems about Hamiltonian actions are really theorems in Poisson geometry, if you see them in the right way. Okay, so a natural question is, do realizations exist? I give you a Poisson manifold. Can you realize it as a quotient of a symplectic manifold by a surjective submersion? Full symplectic realization. And, there's a theorem, was a theorem by Karasev and Weinstein that proved that this is always the case. And, the original approach to proving this was, working locally and constructing the symplectic realizations, locally, and then patching them together using some kind of uniqueness. And this problem was recently revisited, and there are much better ways to construct the symplectic realizations. Now, I'll just briefly mention a formula. So there's a paper by Kreinig and Marcout and Freilich and Marcout that basically says that, if you give me any Poisson manifold whatsoever, I can take its cotangent bundle and the projection, right? As I said, this would be, with a canonical symplectic form, this would be a nice symplectic realization if I had 0 here. Now, if I turn on a Poisson structure here, what you can do is that you can modify the canonical symplectic form here, but keep on having this map as your projection. And that's the formula. That's the way you have to modify the symplectic form. Yeah. Yes, yeah, I will get to that. So, you can put the symplectic form that I defined there, and then show that around the 0 section, this guy is symplectic, and this is a symplectic realization. Okay? And, there's also an explanation for this in terms of symplectic groupoids. I mean, this formula makes sense, and it's also nice to derive it using Dirac geometry that I will speak about tomorrow. Yeah. Yeah, I think many years ago, I taught this course with Mario Skrinic, and this was an exercise that we thought was very easy. And then I think we spent a night trying to do the calculations that for some reason turned out to be more difficult than we thought. And I think eventually him and Yonut found a way to make it work. That became a paper. And then Yonut and Pedro Freilich found an even better way to explain why the computation works using Dirac geometry. But we knew the formula. We knew the formula had to work for some other reasons because of groupoids, blah, blah, blah. But for some reason, it was pretty tricky to. So there's an additional ingredient in the story that I would just mention that refines this question of existence of symplectic realizations a bit more, which is an additional concept that I think I also introduced in the problem set. So if you have a map between 2 Poisson manifolds, or a symplectic realization, say, I'll say, let's say Poisson map. I'll say that it's complete if you can do the following. So given any function M, right? You can consider its Hamiltonian vector field. Using mu, you can pull back this function to S. So this is now a function on S. And you can consider its Hamiltonian vector field, which projects on this one under mu necessarily, because it's a Poisson map. Now the question is, can you flow this for as long as you can flow this necessarily? Suppose that I can flow this until time 1. Is it true that I can also flow this lift until time 1? And the answer is that, that it's not the case necessarily. So so the notion of completeness, is that if this guy is complete, there's an additional requirement that whenever this is complete, then its lift is complete. That's the definition of completeness for a Poisson map. Okay. And so if we refine this question, and by the way, I think that's another problem in the problem set, that this example of quotients by symmetries of symplectic manifolds is a complete symplectic realization. So this is a complete symplectic realization. So you can refine the question and ask, okay, can I always find a complete full symplectic realization? And then the answer is no. And it took quite a while for this to be understood. And it's no because, and the way to understand it is to really understand how this question is related to integration. As I said, integration of what? That's the problem. Okay. So that's why I will get to groupoids now. So there is a close relationship between the problem of finding realizations and an integration problem in Poisson geometry. Okay, so one hint to that, it's even in the very definition of a symplectic realization. As I said, it comes equipped with a second foliation that often leads to a second map into another Poisson manifold. That in natural cases, if you try to construct a symplectic realization, will be the same Poisson manifold. Okay, so you're in a situation where your symplectic realization has two maps into the same manifold. So this looks like this bi-submersions that Camille was talking about. But there's more to it. In the construction, you can also see that M lies in here as a Lagrangian submanifold. And there is some kind of product multiplication type thing that you can try to do. The symplectic realization naturally appears with more structure. And that's the structure of a Lie groupoid. Okay? And I'm not saying that all of them are like this. I'm saying that some natural examples, when you construct them, will have these additional properties. Okay?
Can this construction, this Gaelic manifold construction, can it be seen as a generalization of the Fikes-Cullerton construction of hyperkilometrics in some neighborhood of the zero section of the cotangent bundle of
so a construction of
so there's this construction, Fikes-Cullerton construction of hyperkilometrics.
Okay.
In the neighborhood of the zero section of the cotangent bundle of a Killer manifold.
Yeah, I don't see how they are related. I'm not sure, but yeah, I don't know. I think it's simpler than that, but anyway. So this is the general picture, okay? So if you don't really understand what I'm going to explain about groupoids and algebroids, I just want you to, remember this, is that, there's like this, usual, theory that relates Lie algebras and Lie groups that, we all know about. And there's a far-reaching generalization of this theory to objects known as Lie algebroids and groupoids, okay? And here in between, there's a relationship between Poisson manifolds, which, as we saw, in a way, they generalize Lie algebras if you look at their duals, right? Given a Lie algebra, you can see it as a very special type of Poisson manifold, right? And a Poisson manifold, as I will explain, is a very special type of Lie algebra. Okay, so here in between, there is a theorem, there's a Lie type theory that relates Poisson manifolds as infinitesimal objects to something global. Okay, and the something global is the symplectic group, or the symplectic groupoids. Okay. All right, so let me do, it's like always a very difficult job to talk about groupoids and algebroids with no time, but they've appeared already. So let me briefly I think that, was it Arnold that used to say that a definition is worth, what, 3 or 4 examples or something? So maybe if you don't understand the definition, at least if you understand 3 or 4 examples, that's probably good enough. Okay. Let me do one example. Okay, so what is a Lie groupoid? Okay, so a Lie groupoid, I'll just tell you what the structure maps are. Okay, so we're given like 2 manifolds, G and M, and 2 surjective submersions, S and T, that I call the source and the target. So let's illustrate that with a very concrete example. So consider on a manifold, the set of all paths on the manifold up to, fixed endpoint homotopies. Okay, so there are classes of path on your manifold. All right, so this set has, let me write here the path. So this guy has 2 maps down to M, namely, what, the initial point and the final point. And it doesn't really depend on which curve, right? Because I'm taking them up to homotopy, but with fixed endpoints. Okay, so, okay. Now, on a groupoid, there is a multiplication map, just like a group, except that you are not allowed to multiply any pairs of elements like this. You have to use these 2 maps to decide if they are composable or not. So usually, so they would be composable if the source of one is the target of the other. And that's where your product is defined. Okay, so in this case, if I only give you 2 curves, there's not much you can do with them. Now, if it so happens that one curve ends where the other one starts, which is exactly this condition, then you can concatenate them. And that's an operation, right? Like this group-like operation. And there's something else in the groupoid, which is that an inclusion of this base manifold as a subset of this manifold here as units. Okay, so how do you do that here? So how do you embed M into the space of paths? You just consider a point as a path that doesn't go anywhere. It just stays there. Okay, and of course, if you have a path and you compose it on this side with a path that doesn't go anywhere, you get the same path. Or if you compose it with this path that doesn't go anywhere on the other side, you get the same thing, right? So that's pretty much all you need to know. So this is like the definition, okay? So you have an inversion as well, but let's not worry about all this. And usually people repeat this mantra that a groupoid is a small category or all the morphisms are invertible. I could have said that too, but I don't know if that's too helpful at this point. Okay, but you can think of this guy as the space of arrows. So usually, pictorially, you think of the elements in G, if you think of M, and you think of elements in G as arrows that go from the source to the target. And then you compose them. It's just like you do in categories, right? Composing morphisms. Good. Now, my list of examples. So first of all, in this story, if I set this to be a point, then this condition here is vacuous, right? I mean, everything is composable. And this is just a good old Dirac product. And this becomes a group, a Lie group. Okay, so groupoids over a point are a Lie group. Lie groupoids over a point are Lie groups. Now, another extreme example are just manifolds. So how do you do it with manifolds? So for a manifold, you can take G to be equal to M. So they're the same space. And source and target maps will be the identity. Okay, and what's the operation? Well, basically, this is saying that you can only, compose a point with itself, and the result is itself. Okay, it's a pretty trivial groupoid, but it fits this definition, right? So these are very extreme cases, Lie groups and manifolds, are very extreme cases. And, fundamental groupoids, like the one I described over here, with paths, there's a simplification of the fundamental groupoid called the pair groupoid, which is, given a manifold, you consider just pairs of elements and you compose them like this, right? So source and target are the projections, and you compose them by deleting the guy in the middle. So exactly, if these guys are simply connected, this is the same thing as this. This is what happens to the endpoints of the paths. Okay, good. Let me mention vector bundles as a very simple example where the source and target are the same map. So if you have a vector bundle, you consider the source to be equal to the target to be just the vector bundle projection. In this case, this condition to be composable just says that you can only operate with two elements that live on the same fiber. And what do? You add them. So it's an additive thing fiber-wise. Okay, so in the same way that a vector space can be seen as an abelian group, a vector bundle can be seen as a groupoid, with this abelian operation on fibers. Okay, cool. Now, to have in mind, what are the essential ingredients of a groupoid? If you're given a groupoid, what you should look for? So a groupoid has two main ingredients. So notice that, first of all, a groupoid defines on the base manifold an equivalence relation, which is the following. So, 2 points on M are related if you can find an element of the groupoid whose source is one of your points and whose target is the other point. So this gives an equivalence relation on the base manifold M. Okay, and the equivalence classes are called orbits. Okay, and they turn out to form a singular foliation, with immersed leaves, like the orbits are immersed submanifolds, and so forth. And the other thing you can do is look for arrows that start and end at the same point, because those you can always compose one with the other. So they give you a Lie group. So in a groupoid, you have the orbits, and at each point, you have a Lie group attached to it. It's called the isotropy. Very much like you do when you have an action. Okay. Good. Now, this is all I wanted to say about groupoids. Okay, so to have something in mind is that you have an operation that is group-like, but it's only partially defined. Okay, with respect to these source and target maps. Okay, so what's the infinitesimal version of that? That's what is called Lie algebroid. And Lie algebroids have appeared already in, I think, all the other mini courses up to now. Sometimes explicitly, sometimes in disguise, but okay, so a Lie algebroid, I think the definition may have appeared already, I think appeared in Camille's lecture, maybe second lecture, first lecture, not second lecture. So, it's a triple given by a vector bundle, an anchor map that is just a bundle map from A to Tm, and a Lie bracket on the sections of A. Okay, and then there is a compatibility, which is the Leibniz rule. Okay, so let me give you some very natural examples of that. So tangent bundles, if you take A to be the tangent bundle, the anchor to be the identity, sections of A are the vector fields. and you take the Lie bracket, the commutator bracket of vector fields, and it satisfies this Leibniz condition. More generally, if you have an involutive subbundle, right, then you can take rho to be the inclusion, and because the sections of this subbundle, if it's involutive, it's closed under the Lie bracket, you can restrict the Lie bracket of vector fields to it, and you get another Lie algebroid. So regular foliations are examples of Lie algebroids where the anchor is injective, is the inclusion. Now, again, if you set now M to be a point, then you don't have to worry about the anchor. Your vector bundle becomes a vector space, and sections just become elements of the vector space, and you get an honest Lie algebra. And I think that the most popular Lie algebroid in this week that appeared, I think, in every single mini course so far, with different names, right, is the B, also known as log tangent bundles with respect to some hypersurface, or possibly something even more complicated than that. Okay, so what is that? So if you have a manifold and you have a nice codimension 1 submanifold, smooth, okay, I think Anna had something more complicated than that, but let's stick to this. Then, you know, this space, this vector bundle, which is also denoted in Jonathan's talk like this, has the property that, or is defined by the property that its sections, its sheaf of sections, are exactly the vector fields M, which are tangent to this hypersurface. I think this was also in the first problem of the problem session this morning. Okay, so it turns out that, you know, this sheaf of vector fields is realized as sections of a vector bundle. Okay, and this vector bundle is naturally a Lie algebroid. Okay, because it's closed under the bracket. So it's a sub sheaf of vector fields closed under the bracket. Okay, so that's called the B or log tangent bundle. That's a Lie algebroid. So what do you do with the Lie algebroid? Let me list some features of Lie algebroid, general features. One is that, you know, you look at the image of this anchor map, and that's a distribution, right? At each point, you have a distinguished subspace of the tangent space at that point. The rank may vary, but nonetheless, it turns out that, you know, this leads to a singular foliation. It has orbits. So this distribution is integrable. And you prove that with some kind of splitting theorem as well. Okay? What else? So if you look at the kernel of this anchor map, that has a natural Lie algebra structure. Okay, this should be all like familiar from the case of Poisson manifolds. Now, and that's an important philosophy here, is that you can think of A, of course, as a generalization of the algebra, and then you would like to talk about representations of A and things like that, you can do that. But you can also see A as a replacement or a generalization of the tangent bundle of the manifold. Okay, so from this viewpoint, for example, if you want to talk about forms, how do you define forms on a manifold? These are sections of the powers of T star M. Now, if you replace Tm by A, you should be talking about sections of exterior powers of A star. And these are the A differential forms. Okay? And on this A differential forms, you can define a differential exactly like you do for the differential on ordinary forms, you take these formulas that define the Dirac differential in terms of the Lie bracket. And because we have a Lie bracket in sections here, the same formulas will work, okay? And these will define a differential and turn A forms into a complex, okay? And you can talk about the cohomology of that complex and recover a bunch of cohomologies in all these examples. And you can talk about asymplectic forms. So what is an asymplectic form? Okay, so it's an element, well, it's an element here, which is closed, right, in the right differential, and which is non-degenerate in the sense that as a map from A to A star, it's an isomorphism. That's a non-degeneracy. Okay, so that's an asymplectic form. And you can also have, you also have a generalization of vector fields. So remember, A is Tm. So, multi-vector fields are like this. And in the same way that we extended the vector field, the Lie bracket of vector fields to multi-vector fields, you can do the exact same thing here and define a scalping bracket on A multi-vector fields. And you can talk about A Poisson structures, okay? So let's leave it like that for now. I'll come back to this. Now, let me just mention in 1 second without really explaining it, the fact that just as you can extract a Lie algebra from a Lie group by differentiating, by looking at the tangent bundle or the identity, right? And then playing with left and right vector fields to define a bracket, you can do the exact same thing here and extract a Lie algebroid from any groupoid. Okay? And you say that a Lie algebroid is integrable if you can realize it as the Lie algebroid of some groupoid. And there is a big theorem that we learn in differential geometry or in Lie theory that says that for any finite dimensional Lie algebra, there is a Lie group that integrates it. There is a Lie group that the Lie algebra is the Lie algebra of. Okay? And one of the big differences with this more general theory is that this theorem is no longer true. Okay, so there are Lie algebroids. So another message to be clear. So there are Lie algebroids that are not integrable. Okay? So you have like Lie theorems, if you suppose that the Lie algebroids involved are integrable, then you can like lift morphisms and stuff like that. But, Lie's third theorem doesn't hold. And the precise obstructions were understood by Kreinig and Fernandez, in a by now classical paper from 2003. Okay? Anyway, so now let me go back to Poisson geometry in the last 10 or 15 minutes. Okay, so we stopped. I told you the basics of Lie algebroids and groupoids. Now, how's that related to Poisson geometry? So there are many connections between Poisson manifolds and the theory of Lie algebroids. Okay, I'll show you 3. Okay, the first one for this problem of symplectic realization that I used to motivate this whole story is the most important. Okay, so the first one is that Poisson manifolds are special Lie algebroids. Okay, so I have to give you a vector bundle, an anchor, and a bracket. The vector bundle is T star M. The anchor is the sharp map of the bivector field. And the bracket is just the bracket defined on differentials, so on exact one forms like this. Okay, there's a general formula for it, but I don't need. Okay, I'm just telling you what the bracket is on exact one forms. For general one forms, you can figure out what the general formula is. Okay, and so, the leaves, the orbits of this Lie algebroid are the symplectic leaves. The isotropy Lie algebras are these transverse Lie algebras that I spoke about in my second lecture. And Lie algebroid cohomology is Poisson cohomology. Like Poisson geometry really fits into the theory of Lie algebroids as a nice subset, as a nice class of examples. Okay, that's the first connection. Okay, and as I said, it will be the most important probably for what comes afterwards. Now you can imagine. Okay, now I mean, if you find a groupoid integrating this, what kind of additional structure this groupoid will have. Okay, and that's where symplectic groupoids will come in. But now let me tell you about two other connections that turned out to be very important and I think should be mentioned. So one of them is the fact that just as Lie algebras, when we dualize them, we got Poisson structures which are linear. If you dualize a Lie algebroid, you also get a Poisson structure on the dual. Okay, so here so what I'm saying here is that you can view sections of your Lie algebroid inside functions of the dual as linear functions, right? And I'm calling this map LA. And that's the formula for the Poisson bracket in terms of the Lie bracket and anchor. Okay, what I'm saying is that you can turn a Lie algebroid structure here into a Poisson structure here with some properties. And this turns out to be very important. There's a duality between Lie algebroids and Poisson structures. Now, these two connections that I just described, they're not inverse to one another. Okay, so I told you that given any Poisson manifold, its cotangent bundle was a Lie algebroid, right? And now I'm telling you that the dual of that should be a Poisson manifold again, right? But the dual of that is Tm, is not M, right? And this operation to go from here to here is what is called the tangent lift. Okay, just so that you don't get confused. Anyway, and the second, point of interaction that is more recent, but turns out to be very useful, is to understand several classes of Poisson structures which are generically non-degenerate. They are generically symplectic in terms of Lie algebroids. Okay, so an example is, so if you consider, I just erased this, right? Oh, here, so here. So if you consider this log symplectic, so I defined at some point log symplectic. So you have two n-dimensional manifolds, a bivector field, so that its top power intersects the zero section trivially. Okay, and this also appeared with the name B symplectic in Jonathan's talk, and in the same talk it also appeared with the name B Poisson. Okay, so it's kind of hard to keep track of all the different names for the same thing, but they're all the same thing. Okay, and what is a theorem, and I think it really opened up this field in a way, was this observation that this type of Poisson structures would degenerate exactly on a certain hypersurface. Now, they were in correspondence with symplectic structures on the B or log tangent bundle. So if you replace, the tangent bundle of your manifold by a new tangent bundle that sees this singular locus of your Poisson manifold somehow, then you can see your degenerate Poisson structure as a symplectic one, but on this new place. But the nice thing is that once you do that, then you can try to adapt a bunch of symplectic techniques like Moser's theorem, blah, 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 to this new setup. And many, many, many theorems have been proven with this idea, not only for log symplectic, but for a whole class of, mildly or, generically non-degenerate Poisson structures. B, K, C, scattering, whatever. There are so many elliptic. Now, I think they will show up again. I made a point of saying this because I think they will show up in Richard's mass talk next week, and possibly Marius Kreinig's talk, because he will talk about stable generalized complex structures that have to do with this thing. So that's why. Okay, so again, the message to take home is that some Poisson structures become symplectic once you change the Lie algebroid where they are defined. Okay, so maybe I should mention, I think this program has been developed by a bunch of people. So as I said, I think the starting point was the paper by Eva, Guillemine, and Ana Rita. Yeah, maybe I shouldn't list the name because I'll forget many, but perhaps I should. I think at some point Jeff Scott was involved in this. Maybe Melinda, a student of Cavalcanti, and his student Ralph. How many E's? I don't double. Gotta double all the letters. And Pin. Anyway, there are many names here. Okay, but by now, it's a proper program to try to develop a theory of this generically non-degenerate Poisson structures. Good. Now, a word about symplectic groupoids. Okay, so let me go back to the question which I posed before, which is, if we consider the first connection between Lie algebroids and Poisson manifolds, that was that any Poisson manifold gives rise to a Lie algebroid, the cotangent Lie algebroid. The question is, what happens if you integrate? What's the global object corresponding to this? Okay. And it turns out that the global objects are these symplectic groupoids. So a symplectic groupoid, in 1 minute, it's a Lie groupoid equipped with a symplectic form. Okay, so it's a symplectic manifold with an additional groupoid structure on it over some base M. Okay, and there's a compatibility between the symplectic form and the groupoid structure expressed by this equation, which is a kind of cocycle condition that I could explain another time. Okay, but there's this equation that relates them, and one exercise that could be in the problem set but is not, is an interpretation. There's a symplectic geometric interpretation for this equation that says that the graph of the multiplication, if you look at the graph of the multiplication map inside G times G times G, and you switch the sign of the symplectic form here, this is a Lagrangian submanifold. That's a symplectic geometric description of the compatibility, which is important, which is crucial for the connection with quantization that I'm not talking about. Right? But I think Jonathan at some point in his lecture mentioned this idea that Lagrangian submanifolds should be thought as elements in the symplectic manifold. So this idea is important here. Anyway, so there are several properties that the symplectic groupoids have that are derived from this one single condition. The inversion is an anti-symplectomorphism. The source and target fibers are the symplectic orthogonal of one another. Many things happen. And the most important one is that if you have a symplectic groupoid, then the space of units, M, immediately inherits a Poisson structure, which is uniquely defined by the fact that the target map is a Poisson map. Or in other words, you get a symplectic realization. Okay? So by integrating, so what's the upshot here? So let's say you're interested in symplectic realizations. Okay, it's a natural problem in symplectic geometry. Once you realize the Poisson manifold as a Lie algebroid, and you integrate this Lie algebroid, you find your symplectic realization, which is moreover complete. Okay? And another property is that any symplectic groupoid, turns out to integrate, the Lie algebroid of its base Poisson manifold. And, this is almost, an if and only if modulo some, source simply connected issue. Okay. And one can, the way to show that these complete realizations don't exist in general was actually to prove that their existence was equivalent to the integrability of this Lie algebroid, and understanding that this Lie algebroid may not be integrable. I told you that in general, Lie algebroids are not integrable, but even those coming from Poisson manifolds are not integrable. Okay, so that was like the path. So this theorem was, I think, first. So this was like an open question that was settled by Kreinig and Fernandez. And more recently, there's another argument. So they use their obstructions and stuff. And recently, there's another argument that is more direct by Daniel Alvarez that was published last year, like a very short argument to prove just this equivalence. And as I said, it's not always true that we can integrate the Poisson manifold. Okay, so if I have 2 minutes just to wrap this up. Okay, so this was pretty much all I wanted to say. So there are various examples of Poisson manifolds that are integrable, and you can find their symplectic groupoids. So for example, in the trivial case, right, remember that in the trivial case, I said that the cotangent bundle itself, with the canonical symplectic form, was a symplectic realization. And this is, in fact, the symplectic groupoid integrating the zero Poisson structure. And the groupoid structure is the vector bundle structure, is the fiber-wise addition, which says that the canonical symplectic form is linear in the sense that it satisfies that compatibility equation for the linear structure here. So that's one. So any symplectic manifold is integrable. You just take its product, and there's this pair groupoid structure there. That's very simple. Whenever you have a symplectic, a Poisson manifold, which is acted on by a Lie group in a nice way, preserving the Poisson structure. So you saw this problem that this has a quotient Poisson bracket. Now, the story here is that if you happen to know a symplectic groupoid, that this one is integrable, and you consider its canonical integration, the symplectic groupoid integrating it, then you can always lift the action of G to the symplectic groupoid over here, and naturally, canonically, there will be a moment map at this higher level, at this upper level. And then you can do Marzi-Marzi reduction of this guy as a symplectic manifold, right? And this will be the groupoid integrating this guy. Okay, so if you know how to integrate a manifold, you know how to integrate all its quotients in this way. And the fact that there is this canonical moment map when you lift the action to the symplectic groupoid is reminiscent from the fact that the same is true for cotangent bundles. If you have an action on a manifold and you lift that to the cotangent bundle canonically, there will be a canonical moment map there, right? So it's exactly the same thing that goes, that carries through to symplectic groupoids in general. So let me make one comment. Sorry that I'm going a few minutes extra time, but I just want to wrap this up. So I want to make a comment about duals of Lie algebras, because as I said, I already showed a symplectic realization for the dual of the Lie algebra. but this symplectic realization was already its symplectic groupoid. And here the source and target are left and right translations. And the multiplication comes from the adjoint action. Okay, but remember, but this guy is also a symplectic groupoid, and this was with the canonical form. And this guy, because of this simple example, it's also the symplectic groupoid of G with a zero Poisson bracket. So this is an example of, a symplectic manifold that is a symplectic groupoid in two different ways. So this is what is called a double symplectic groupoid. And I just want to mention them because they will play a key role in Gualtieri's talk next week. Okay, this double symplectic groupoids. It turns out that now they are showing up in relation with generalized scalar geometry. Okay, so I just wanted to mention that these objects exist. So Poisson Lie groups are always integrable. That's a result of Lewin Weinstein. Poisson homogeneous spaces are always integrable. That's a recent result that I proved with David Iglesias and Jianhuan Lu. And log symplectic manifolds are always integrable, and you can understand their groupoids. Gualtieri and Travis Lee did that. Now, just to finish, final remarks, just like various applications of symplectic groupoids in Poisson geometry. So let me just mention that, one of the constructions of the symplectic groupoid of a Poisson manifold has to do with field theory, with physics, the Poisson sigma model. That's like Cattaneo and Felder. That there's an entire program of quantizing Poisson manifolds by doing a type of geometric quantization in the sense of Jonathan, but more or less a variation of that for the corresponding symplectic groupoid. That started with Weinstein and then Eli Hawkins and now Bonecki and collaborators. Bonecki is around. So you can make sense of any Poisson map as a moment map if you now understand what are actions of symplectic groupoids. So you can kind of, extend all this Hamiltonian theory to symplectic groupoid actions. And finally, it's a very effective tool in Poisson geometry, symplectic groupoids, to calculate and prove the vanishing of certain cohomologies, by doing averaging and things like that. And this is used, for example, in the geometric proof of this Kahn's linearization theorem. And finally, there's an entire program also of understanding properties of Poisson manifolds by knowing properties like compactness properties of the corresponding symplectic groupoids. You can say a lot of things about the Poisson manifold. If you happen to know that they admit a symplectic groupoid, whose source and target are proper, or the total space is compact, or whatever, many properties. Okay, and you can go beyond, and I will speak about that tomorrow. Thank you. Sorry for going over time.
Okay, thank you, Enrique. So that's been a very long morning.
Yeah, sorry about that.
But do we still have any quick questions? Yeah, please.
How much is known about the classification of symplectic realizations of given Poisson manifold?
Yeah, I think not much is known. Yeah, I think that they have some uniqueness property. If you happen to know that there's a Lagrangian embedding, or depending on the dimensions, blah blah blah, there's some uniqueness property. But I'm not sure you can say much in general about how to classify them. Yeah, maybe in specific cases you can.
Any other questions?
Is there some kind of obstruction known for integrability besides Poisson manifolds, just for some Lie algebroid?
Oh yeah. So they are very precise. The integrability, they depend on the kind of discreteness or uniform discreteness of certain groups that you can define for any Lie algebroid. So yeah, the obstruction is the discreteness or uniform discreteness of something. Yeah, so that's known. Yeah, that's like the Kreinig-Fernandez theory.
So, in most of your integrable example, the ambient space of the symplectic groupoid is a cotangent bundle of something.
Yeah, in the example, but yeah, that's far from being always the case.
Yeah.
Yeah.
So, okay. Don't you know any necessary condition on the Poisson?
Yeah, that's actually a good problem, a good question. Yeah, I'm not sure if there's a clear criterion for that, but I think that Alan at some point even singled out this class of Poisson manifolds, saying that they were of exponential type or something like this. I think they were important for quantization. But I honestly don't remember if there is a clear criterion for you to say, oh yeah, you can realize, you know, the symplectic groupoid can be, you can put something in the cotangent bundle. And, yeah. Yeah, I think it's, yeah.
Like the quadratic one. And,
Yeah, so yeah, but there are many cases that it's not, that they are not given by cotangent bundles. It's like for Poisson groups or homogeneous spaces. Yeah. So they are not cotangent bundles in general. For example, in the case of Poisson group, could be just the product of the Lie group and its dual group. Yeah.
Okay, I don't see any further raised hands, so let's thank Enrique again